Good morning and good evening, everyone. I'm Jinfeng Zhang, a researcher from Recon EIP. Today, I'm going to hold a nice TrustML Young Scientist seminar. Before that, allow me to briefly introduce our Recon Center to our valuable guests, Ivy and Chen. Today, the full name of Recon EIP is the Recon Center for Advanced Intelligence Project, EIP. EIP was founded in 2016 as a research center for the MAXT EIP project. EIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama, and it has to the AI fundamental technology and its real-world applications. EIP encourages collaboration with various researchers and engineers in related fields. We would be very grateful if our guests and you, audience, can visit us in our Nihon bases in the center of Tokyo in the near future. Next, let me hugely welcome the Ivy Schwarzschild is to present his talk in our center. So let me briefly introduce him first. Ivy is a PhD student in the Applied Math and Scientific Computation program at the University of Maryland. He's advised by Tom Goldstein on his work in deep learning. His interest in data security and model vulnerability has led to work on adversarial attacks and data poisoning. Other projects of his focus on investigating neural network ability to extrapolate from easy training tasks to more difficult problems at the test time. Hello, Ivy. Can you share screen?
Sure.
Yeah, you can get started your talk right now.
Okay. Good morning and good evening. Thank you for that introduction. Thank you for having me. My name is Avi Schwarzschild, and as was just said, I'm a student at the University of Maryland, advised by Tom Goldstein. And today I'm going to talk to you about a project we did on data poisoning, where we asked the question, just how toxic is data poisoning? And we designed a unified benchmark for backdoor and data poisoning attacks. I will try to speak slowly and clearly, but by all means, please interrupt me if you have questions, or if you want me to repeat something. I don't mind being interrupted. So let's get started. We're going to sort of break this talk into 4 sections. They're not so clearly delineated later on, but I'll give you a little bit of background. We'll try to answer the question why we need benchmarks. We'll try to answer the central question of the day, just how toxic is data poisoning? And then I'll present the details of our uniform benchmark. There are a few QR codes on slides here and there. On the left side, it'll be a link to the paper. And I think there's another one later on, which is a link to a GitHub repository. But all of this should be available if you Google the title of the paper. To start with background, we're going to talk about what data poisoning is. I think probably in this audience, people are familiar if you're thinking about trustworthy machine learning. But we'll define a few terms so that we can all be on the same page. And then I'll try to motivate why poisoning is important to think about it all. So what we mean when we talk about a data poisoning attack is something where the training data is manipulated. This is usually in the form of manipulating the inputs, or at least in the cases we're going to talk about today, it is. There are poisoning attacks where you're manipulating the labels or the targets as well. What we mean when we say that these perturbations are clean label is that to a human observer, or maybe within some norm, they still look like they did before we manipulated them. And the goal is for the attacker to control the test time behavior. So this picture on the right comes from a paper from Ali Shafahi. And the idea is that this decision boundary without the poison is this dashed line, and it would pretty well classify the blue and the green data. If, however, we add this poison green X, and then we find a linear classifier, we're going to slide that decision boundary over to the solid line, and then we'll misclassify that target data, that blue dot, while still correctly classifying the majority of the data. So this would be a very small 2D example, and it would be hard to discern that the model was poisoned because most of these blue dots are still labeled correctly. This is sort of it's a depiction. This doesn't come from a real experiment, but it's a depiction of what the attacker would love to do. If everything works out perfectly, this is what would happen. And these attacks come in two flavors or two styles. One we call backdoor attacks. I'm still going to use the umbrella term data poisoning because backdoor attacks manipulate training data. We can think of that as poisoning, but they have a trigger at test time. And I'll show you a little bit in a second. I'll give you some more detail. Our second flavor is triggerless attacks. So that is where you maybe have a single target. In theory, it could be more than one, but again, in all the work I'm going to discuss today, it's a single target. And the idea is that that target input will be misclassified without changing the input at test time. So with backdoor attacks, we have to manipulate the input even at test time, in addition to changing all of the training data before the model was trained. And with triggerless models, we don't. All the work I'm going to talk about today applies to neural networks. Neural networks have this, they're very brittle, this property of being fragile, unlike a lot of classical methods. So linear things, even though this picture on the right comes from a linear classifier in a 2D plane, linear classifiers tend to be a little more stable in a lot of ways. I'm not going to talk more about that, but it should just be noted that anytime I talk about a model or training, the thing we are training is a neural network. Okay, a little bit more detail on these flavors. Like I said, backdoor has a trigger. So that image on the top is an airplane in CFAR10, and that would be an airplane if it was passed through our network as is. Again, this is at test time after training has happened. But if things were poisoned and if the attacker is doing well, then by adding this small patch at the bottom right, so that's what we call a trigger, you would get a desired output. And this is a whole category of attacks exist like this, where you would be manipulating the test time image itself by adding a trigger. And this doesn't only apply to images, but again, that's something that for my talk today, we're only going to look at image classifiers. Generally, poisoning has been studied in a lot of domains, including language and speech. There's also triggerless. In a triggerless attack, this clean test time image doesn't need to be modified, and it will just always get mislabeled. In my opinion, there isn't a clear winner here. Sometimes you want that trigger so that you can take one image and sometimes get one behavior and sometimes get another. It gives the test time behavior a little more control. And sometimes you don't want to worry about manipulating things with a trigger. For example, if you're expecting to encounter this airplane in real life, it may be very hard to put a trigger into the image in whatever pipeline your victim is using. Okay, a little bit more background about why poisoning matters so much. There's a survey, Data Set Security for Machine Learning, that covers data poisoning, backdoor attacks, and defenses. This came out in 2020. It was just recently accepted to TPAMI. I'm a co-author of this work, so I left a QR code. This is a little self-advertisement, but there are a couple other surveys from 2020 and one from 2022. And all of these are comprehensive review papers. I'm going to borrow the word from the second title. I like that. There is so much work on poisoning right now that 3 different groups of people have felt there's enough work to fill a review paper. So this should tell you that at least the academics care about poisoning, right? At least there are people writing papers and publishing in journals, and they care enough about poisoning to keep producing work. But what's really important is that this is also really worrisome to industry practitioners. So there was a survey done in 2020, not a survey paper, but an actual surveying of industry practitioners who use machine learning or interact with machine learning models. And they were asked about which vulnerabilities they're worried about. So things like adversarial attacks and data poisoning. And data poisoning was by far the top choice of all these industry practitioners of their biggest fear. When they employ their models and they need to make sure that they work well, poisoning comes to mind as the biggest threat. So this should hopefully convince everyone that poisoning matters. Poisoning is a little bit scary. I'm not trying to say that the world is falling apart and that all the models you interact with have been poisoned. I think we'd probably be hard pressed to make that case, but it is at least threatening to all the people in industry, to a lot of people in industry. A little bit more background, and I'm not going to give a lot of details about this, But the particular attacks, so these papers, these 4 papers, and I'll show a couple more titles in a moment, but are papers that outline an attack method. Feature collision is actually was proposed in the paper that I borrowed that graphic from before, Shafahi et al. 2018. And that's a method in which you try and move the features by changing the inputs. So each of these attacks, feature collision and convex polytope, are triggerless, and clean label backdoor and hidden trigger backdoor are backdoor attacks in their names. Each of these attacks has, let's say, a suite of experiments done in the paper and an algorithm that they propose. And I'm not going to give you all of those nitty-gritty details today. I think for this talk, it's sufficient to know that these are 4 different algorithms. And in fact, there are 2 more, one called bullseye polytope and one called witch's brew that we're also going to mention. The separation here has to do with which ones we use in our very in-depth analysis. So we'll get to that in this talk. But the top 4 we're going to focus on. And really the important thing to take away from this slide is that these acronyms, FC, CP, CLBD, and HTBD, those are 4 different backdoor or data poisoning attacks. And so when you see them, we're referencing either the papers that propose them or the actual methods proposed in those papers. So there are a lot of them. Like I said before, there's enough poisoning work to fill 3 review papers. Well, these are some of the attacks that exist out there. And all 6 of these works addressed image classifiers. But there is a whole body of work on non-image data as well. And again, I'm not going to mention that today. Okay, I think that's enough background. I think we can move on to our question of why we need benchmarks. In general, in computer vision, or in deep learning, I suppose, we have a lot of benchmarks. If you want to test an image classifier, you might pick a data set that's small, like MNIST or CFAR10, or maybe you have a lot of resources, you're training a big model, you might move to ImageNet, and you know that if you use that test set from those data sets that are publicly available, you're testing your model on the same data that someone else, or actually that a lot of people have, right? However, in poisoning, our literature lacks a standardized test scenario. So we will discuss exactly what a test scenario entails. Like I mentioned with classification, that's just a fixed data set, right? The CFAR test set, the CFAR10 test set is fixed. It doesn't change. And if you can get 98% on that and I get 97% on that, in addition to both having very good models, we would know that you're better than my model. In poisoning, it's a little bit unclear what a standardized test scenario should look like. In part, this is because the training is involved. So it's if you want to reduce the attack to what I think is maybe a nice contained definition, then the attack constitutes a batch of training data wherein you have manipulated it in some way. And the test should include training and evaluating the model on your target. If we put training in the test scenario, then we're leaving all kinds of hyperparameters that we either need to fix or need to have some method for accounting for how they might be different. So we can talk a little bit more in depth about the papers that I talked about earlier. This table is complicated. We're going to spend a little bit of time on this, so don't feel any pressure to figure out what all my wacky letters mean. But let's start with talking about each row is a different attack. So again, those letters FC, CP, CLBD, and HTBD, those come from those papers: feature collision, convex polytope, clean label backdoor, hidden trigger backdoor. And this is an assessment. We've charted all the variability in the experimental design. So let's start all the way on the left, and we'll make this a little bit more clear. We could ask the question, when they trained the victim model after the data has been manipulated. So we know, I should have said this first, but we know that the data is manipulated in a different way in each of these papers. That's the proposal, right? Feature collision is a method to manipulate the training data, and convex polytope is a different one. So after they've manipulated the training data, we're interested in seeing what they did differently. So we can ask the question, did they use data augmentation? Did they normalize the data when they were training? Now, you might think maybe this doesn't matter so much, but these are training setup parameters. These might change the model a lot. In fact, we know about these two things, that they, generally speaking, boost classification performance. Maybe by making a better model, you make a more vulnerable one or a less vulnerable one. I won't even speculate as to which direction, but if we're not doing the same thing each time, it doesn't feel like such a fair comparison. So the red X's indicate that they did not use this technique. For example, clean label backdoor, that second to last column, did not normalize the data. However, they did use data augmentation when training. And you see in these two columns alone, we have almost every combination. We can move on to ask the question, which optimizer was used during training? And I've left the column title as SGD. So where there's a black check in the bottom two rows, SGD was used, stochastic gradient descent. And the red X's, although this isn't written explicitly, you can take my word for it. The red X's indicate that those papers used Atom. And this is another choice we make every time we train image classifiers about which optimizer to use. And there's reason to think this also might make a big difference. Perhaps SGD is a little more robust to poisoning techniques. Well, that would mean that if one paper used SGD and the other didn't, we can no longer compare their reported accuracies really on a level playing field. We can move along to transfer learning. So it turns out that in all four of these papers, they're really interested in transfer learning setups. They take a trained feature extractor and they do something else with it. And what they do with that feature extractor actually varies a lot. So the first column tells you if they considered at all the case where you freeze that feature extractor and you fine tune the last layer on whatever data set you're on your poisoned data set, on your downstream task. And it seems that most of them did, but not all of them. There's also the question of, did they consider end-to-end fine tuning? So you take your feature extractor from some upstream data, you tack on a new randomly initialized linear layer at the end, but then you train the whole network start to finish. That was also considered in two papers, but not the other two. And then the last thing is, without transfer learning, we might be interested in whether these papers considered the from scratch training scenario, where you just have a randomly initialized network and the only training data you have is your downstream task and it has been manipulated by the attacker. This is maybe even a bigger deal than the other training setups, right? Whether you normalize your data or not, perhaps you could study whether that actually increases vulnerability or decreases vulnerability. But these are completely different threat models, right? From scratch training, only one paper considered this, and that paper only considered that column, right? The clean label backdoor. So they're not even saying that their method is good for transfer learning. Does that mean it's bad for transfer learning? It's kind of hard to compare then to the other papers which didn't consider this. I think that this is kind of perhaps the biggest gap in how we compare, how we measure the performance of these methods. I know you may be asking yourself, well, these papers came out in some order. Does the later one check back with the earlier methods using their scenario? So for example, I think hidden trigger backdoor is the most recent of these four papers. Maybe they picked this row intentionally. They wanted to do data normalization and data augmentation, and they didn't want to do something else. And maybe they used that setup and ran that on all the previous poisoning methods to do their comparison. That would be nice. Unfortunately, that's missing from some of these papers too. And I'm not trying to pick on the authors. I have certainly written papers myself that don't do things in as thorough a way as we might want. But after the fact, as someone who arrived to the data poisoning space after these four papers were written, this really struck us. So let's keep going with our table here. There's also the difference in threat model. And I'm using threat model here really just to distinguish between white box, gray box, or black box. And that's sort of a question of how much information the attacker has. So in the white box setting, they not only know the model they're attacking, but they know the weights. In the black box, maybe they don't even know the architecture or the data that's going to be used, stuff like that. And this is another big difference, right? There's a practical question. Does your attacker have access to the victim's network? If they do, perhaps different strategies work better. So again, it doesn't bother me, or it shouldn't bother you, I should say, that a variety of these things has been studied, but there's very little consistency. It makes it hard for us to know if convex polytope is in fact a stronger attack than the feature collision attack. We have two more columns to move through kind of quickly. Are ensembles considered? So if your victim uses an ensemble of networks, often that increases robustness. Often that makes you a little bit tougher when it comes to manipulating data, right? You'd think that if maybe in the case of evasion attacks, if you're just going to change some test time data a little bit and try to push it right over the decision boundary, well, if it goes over the decision boundary for one model, but you're doing an ensemble of 5, that one might get outvoted by the other 4, which are maybe robust, that type of perturbation. So the same is true for poisoning. If you're changing training data to manipulate your architecture or manipulate your model, if you have 5 different architectures, maybe one manipulation doesn't work for all of them. So this is also an important thing to consider. And lastly, and maybe I shouldn't have picked one of these as the biggest, because this is also, in my opinion, a large difference, but how big is the perturbation allowed? Can the attacker change the image completely, or are they confined to a very small epsilon ball? And it turns out that in feature collision, they didn't consider an epsilon bound, they just penalized the L2 distance. So they just looked for inputs that were similar to the clean inputs. And they don't tell you what the norm is. They just ask that it be similar in an L2 norm sense. That's a little bit atypical for computer vision security. Generally, we try to quantify these things. And these other 3 papers, in fact, do that. They restrict the perturbation to be some number out of, these are all out of 255. But you see 3 different numbers here. So again, would the clean label backdoor attack do better if its epsilon was 16 instead of 8? In other words, if you were allowed to change the inputs even more? Probably. Certainly, there's reason to think it would be different. Okay, so before we leave this table, now that we went through it all, the most important takeaway is that no 2 rows look the same, and certainly all 4 rows don't look the same, right? We have a complete scattering of red X's and black checks. So all of these decisions that let's say that a scientist makes before they do these experiments, and that's, I think of these authors as scientists, they made very different decisions about how to set up their experiment. And again, that's not a problem, but it makes it hard as a reader after the fact to compare these methods. So it would be nice if we had a benchmark, right? If we had one standardized, basically you could think of this as a row here of checks and X's that we fixed, and we used that for all the models. And if we do that, then we can really try and address the question of how strong these models are, right? Until we standardize that, it's hard to know. How do you measure the strength if you're using 2 different tests? So the central question of today, and I told you we'd come back to this, is just how toxic is data poisoning, right? We have all of these techniques for manipulating data, and we know that the way they were tested in their original papers is inconsistent, and maybe each of those design questions doesn't affect the outcome, right? Maybe data normalization turns out to be irrelevant, but if we could determine that, then we could answer this question. And I'll just give you a little bit of a spoiler. I'm not going to measure how toxic each one is until the very end. That's the benchmark. But in this section, we're going to talk about why that measurement is complicated, right? Why is it confusing? What makes it difficult to say this is a strong attack or this is a weak attack? So attack success depends on experimental design. Well, from that table before, we talked about, I think all of these, certainly most of them. It does depend on optimizer. That's something we found. It does, in fact, depend on data augmentation. This one perhaps makes some sense, right? If you're doing data augmentation, then maybe how you manipulate the data is more or less important. You might ask if it depends on victim architecture. We find that it does. So that an example there is like, is the victim who's training their model and doesn't know about the perturbed data, are they training a ResNet 18 or a VGG model? That's a particularly interesting one to me personally, because if I was sitting down to solve a real question in practice, I might pick an architecture that does well on some validation set that I have, but there's no reason to think that should be the same, right? Data augmentation, let me make that point a little more clear. Data augmentation, you should probably assume that your victim is doing it, right? If you're keeping up with the field, if you read a lot of deep learning papers in computer vision, you know that basically data augmentation makes things better, right? Makes things a little more accurate, excuse me. So although we do find that it changes the outcome, the attacker might assume that the victim is doing something somewhat standard. With victim architecture, it's much harder. We might think of ResNet 18 as your favorite model, or perhaps you have a different favorite model, but when it comes to attacking someone in the field who possesses real data and they can choose using some holdout set or some validation set what system to use, and they're really just after their best generalization, right? Their best model. They might do wacky things to the architecture. Maybe they even do some experiment and they find out that a ResNet 23 works well for them. They concoct some new block and it has a different number of layers. So the victim architecture is, I think, a really difficult thing to predict, right? You don't know exactly what your victim is going to choose. There's also perturbation norm. I think this is maybe an obvious one, right? It's not surprising that if you're manipulating data, a larger manipulation is going to help you more in terms of like the game you're playing here as the attacker. But it's also a difficult one to predict, right? The reason that we bound the perturbation norm is to make sure we stay under the radar. The attacker doesn't want their perturbation to be so obvious. And it's a little bit hard to know what perturbation in an L infinity or in an L2 sense is not detectable. It might even depend on whether the attacker is doing something to try and detect perturbations, right? There are defenses to these data poisoning attacks, which actually I should have mentioned earlier. There are many defenses. Data poisoning attacks and data poisoning defenses have sort of been published one after the other for a long time. So there's a whole bank of things you can do as a victim to try and mitigate these attacks. But without knowing what and we're not going to really consider them in a quantitative way today, but they're important for this point. Without knowing if there's some defense, some line of defense, knowing which perturbation norm to pick is, I wouldn't really know how to go about that decision process. So it's not surprising that it affects the outcome, but it is a really big variable as the attacker. There's also the transfer learning regime. And this, again, I think is not surprising. And it might even be predictable. Maybe if your victim is a very small business with not a lot of resources, maybe you can estimate or make a good guess that they're probably downloading some pre-trained image feature extractor on ImageNet that was trained with resources they don't have. Or maybe you're attacking someone that you know is going to train everything from scratch because they're doing a very weird task where they're trying to discern, different species of butterflies, and it turns out that feature extractors trained on image classification, generally speaking, don't do well. So the transfer learning regime might be predictable, and it certainly is not surprising that it makes a big difference. There's also data set size. We're going to get into this. We'll spend a few minutes on it in just a moment. But the question is, how much data is your victim using? Maybe they are using 100 images to train on. I know it doesn't sound like a lot, but if they're only using 100 and you manipulate 5 of them, you've changed 5% of their training data. Maybe that's a lot of data. Whereas if they're training on ImageNet and they have 1 million images or more, or maybe they're even doing, some data augmentation and it feels like they have 2 million images, then if you change 5 images, you might not influence their model that much. So data set size is also something that was inconsistent across papers that we looked at. And it's not surprising, again, in my opinion, that it makes such a big difference. And I think in terms of predictability, it's kind of in the middle. Maybe if you know something about your victim, you might know how much data they have. Certainly in the case where you just imagine that your victim is scraping images off the internet, you don't know how many images they scraped, right? So one common discussed threat is that somebody out there is scraping all the images of dogs off of Facebook or Instagram or whatever other social media site, and they're going to train a dog classifier, and you're hoping that your dog always gets classified as the wrong breed for some reason. So you may poison all of your images that you upload of your own dog. This is perhaps more convincing when it's discussed about facial recognition, but since we're not doing facial recognition models today, I'm going to stay away from that. But you can imagine modifying all your profile pictures to hopefully evade the facial detection systems that get trained on internet data. In that often discussed threat, you don't really know how much data your victim uses. So maybe data set size is hard to predict. There's also a threat model, as we discussed before, black box versus white box. This doesn't have the prediction question. You either have access to your victim's model or you don't. As the attacker, you would know that. And it's not surprising that this might influence which method you would choose to use as your attack. But again, you would have this information. So perhaps that one's not so such a big deal as long as we pick one and we compare across them. There's also the base target class pair, excuse me. We're almost done with this list. But that's to say, if you want to move all of your frogs into the bird class, do you have to modify the birds in the training data? And does the same method that works well for birds and frogs work well for houses and planes? Turns out it does not. And lastly, there's the specific image of target objective. So this really only applies to the triggerless ones. The triggered attacks are designed to work on any test time image with the patch, with the trigger. But if it's a triggerless attack, are you picking a single target image? And let's say you're trying to move your blue 1996 Toyota Corolla. You have a picture of that car, and you're trying to make sure that that looks like a house to this classifier. Is that still going to work if you have a slightly different picture of that blue car? So if you are sensitive to that, it might be a very weak attack. Okay, I know that I just spent a lot of time telling you which of these I think is a big deal or which is predictable on the part of your attacker, but let's just pick two of them and I'll give you some visual examples. Perturbation norm. So on the left is an example of a cat. I hope it's not too large to make out, but the top left is a cat from the CFAR10 dataset, and the bottom left is the poisoned version. So if you run the feature collision attack on that cat, as it was described in the paper, what you get back is this bottom left image. Now that paper claimed to be clean label, so that if you looked at the manipulated data, it would still be identifiable as a cat. I can't speak for those authors, but in my opinion, it is no longer a cat. The right-hand side comes from the convex polytope paper, where an airplane is manipulated. And again, with CFAR10, it's a little hard because things are already very pixely, but I think it's safe to say the image on the bottom is not clean label. It's at the very least discernible that it has been modified, right? If you just looked at all the CFAR10 images, that is noisier than any other CFAR10 image. So it's easy to detect. Maybe I won't make the binary claim of is it clean label or not, but I think that these are very large perturbations. So we wanted to pick for the benchmark, we'll get to that in a moment, but we wanted to pick a perturbation norm that we felt reflected the community's standards for what is clean label. And that comes from the adversarial attack literature. I'll give a little bit more detail when we get to that. The other thing I wanted to talk about, which I said I would spend a little more time on, is dataset size. So this chart comes from a large array of experiments. Let me break them down. For each method, so each method is a different color, as mentioned on the bottom right there. For each method, we created poisons, and then we trained a model with a lot of different size training sets. So we took 100 images, so that's 10 training images from each of the CFAR10 classes, and we poisoned 1% of them, or I guess if 1% of them. So we started with 100, and the attackers allowed to manipulate a single image, and that's this left edge of the plot. So you see, oh, it might have had to be 2. I'm just thinking now about how convex polytope works. Let's say we did 5% because maybe I'm misremembering the details. So you're allowed to change 5% of the data. So when you have 100 images all the way here on the left, convex polytope is by far the best, right? It's 100% effective or near 100% effective. And the shaded regions are plus or minus a standard error. So we did a lot of experiments here. And you see the ordering when you have very small training set sizes all the way on the left. The orange is at the top, convex polytope. It's better than feature collision, which is better than hidden trigger backdoor, which is better than clean label. But as you increase the training set size, so you hold the fraction of the data constant, you're always allowed to perturb 5%, let's say. And again, I might be misremembering that number. So in the paper, it has that detail correct, but you hold that constant, you can always change 5% of the data, but we have more data. So when you get over to, let's say 20,000 images, that's the size of the training set on the x-axis. All of a sudden, the blue and orange curves cross. If you have a lot of data, convex polytope doesn't do as well, and feature collision starts doing better. And all the way on the right-hand side, we've almost reversed the ordering of these. If you give the entire training set of CFAR10 to our attackers, then the clean label backdoor attacker wins, right? With, I think it's upwards of 90%, and then followed by feature collision, and then hidden trigger backdoor. All of a sudden, convex polytope is the worst. So I think it's safe to say from this plot that all the methods are sensitive, maybe some extra sensitive, but they're sensitive to the size of the training set. And again, this is for holding the percentage of data manipulated constant. This lends a lot of, it really begs the question of how can we compare these if we're using different data set sizes or different data set fractions, right? Although this doesn't show experiments where we change the data set fraction, the point is the number of poisons might be a really big variable in how effective your method is. So one thing that comes up when I talk about this plot, a lot of people ask me why. It's actually hard. I think that's an open question about why these are all so sensitive. I think with convex polytope, one big issue is that the optimization requires ensuring that all these data points form a convex polytope in feature space. And without getting too much into the details, that optimization problem, or at least the algorithm implemented in that paper, struggles, I think, with so many data points. One way to think about this is if you require that the target is inside of a convex polytope of some points you're randomly allowed to place. So this is a little bit of a simplification, but if you just randomly place them, then if you have only two, you're going to get to a point where those 3 points are collinear. That's like a pretty big constraint. So if you have a linear classifier in that data space, you're going to end up misclassifying the target. But if you think about this with lots of them, you may end up with a whole cluster down here and one over here. And maybe even there's a way, probably not with a linear classifier. In fact, that might be proven in the paper, but with something very mildly nonlinear, if you'll let me use that non-technical term, you might be able to slice this feature space sort of gently with a curve that correctly classifies all those points. Forgive me if that hand demonstration was complicated. Really, I'm trying to make the point that understanding the dynamics in this plot on the right-hand side is hard. It's hard for us. But it certainly makes the point that these methods are all very sensitive to changes in the experimental design. Okay, so just how toxic is data poisoning? How can we compare their performance across changes in the experimental design? On the left here, we're going to start with the baseline. We're going to fill out to the right. That's what's about to happen. But these are the baseline numbers. And I just want to go over them super quickly. Feature collision, what we mean by baseline is actually our best ability to recreate the scenario in the paper for each of these. So these are not a consistent test bed, but we're going to start each of them with their own baseline. And those horizontal bars in color that match the color of the vertical bars will be carried on to the right. And so those represent those baseline numbers. And each of these columns now is something we changed. So we added data augmentation in the second column, and all of these attacks got less successful. We switched to SGD from Atom, and all of these attacks got less successful. We used a ResNet 18 as the victim, and most of them got less successful. we did a transfer learning scenario that was consistent and in fact boosted the performance of convex polytope while crushing the performance of the other ones. So as we make each of these changes, right, epsilon is 8/255. That's just leveling the playing field, and nothing did as well as it was supposed to. The black box case is, as I mentioned before, where the attacker is not allowed access to the victim's architecture. And by the way we enforce that is we just use an architecture at test time that's different from the one we used when we formed the poisons. So it's kind of like a 0th order approximation of black box. That also hurt a lot of them. And the last one is flip. We didn't do this for the backdoor attacks because they have a trigger. So flipping the test image doesn't matter as long as the trigger is correct. But for the convex polytope and feature collision, you pick a single target. Like I mentioned before, if you imagine you have an image of your blue car, if you just take a mirror image, so it's kind of like the mildest change you could make, right? I said, imagine you have a different photo. I was thinking about like a different angle completely, maybe the front bumper instead of the side of the car. If you just take a mirror image of your test time target image, you might think that doesn't make a difference, and it turns out that makes a really big difference. So this is sort of the central finding, or a central finding. Maybe there are about 3 or 4 things that I think are central in this paper, but this is a big one. These are all actually very sensitive. So when I said before, I'm not going to answer the question, just how toxic are each of these methods? At this point, we're just pointing out that measuring that toxicity, measuring how effective each method is very complicated, because each change you make to the experimental design has the potential to change the performance. So again, the numbers on the y-axis are just not that important. Really, I just want you to note the variability in the height of all these bars. Okay. So to answer this question, just how toxic, we need a uniform benchmark, and we're going to talk about that next. Here's a QR code to the code. Again, if you're bored with this talk, follow it and go browse the GitHub repository. If you want to go back to it later, it's linked from the paper, so there's ample ways to find it. But we're going to introduce uniform testing scenarios. That's what I told you we were missing before. We're going to use CFAR10 data and tiny ImageNet data. If you've played with tiny ImageNet data before, you know, but if you haven't, it's I believe it's a subset of ImageNet. It is also a smaller resolution. And the goal of picking these data sets was that this is accessible to academic labs. We at Maryland struggle sometimes when the methods we want to compare to have tested themselves on data sets that are out of reach for our resources. So that was important to us. We're going to look at white box and black box tests. So if you haven't figured out by now, we're not coming up with a single number. We're going to actually do a lot of tests. And we're going to do transfer learning and from scratch training. So let's talk about evaluation metrics. And that's sort of a combination of the training scenario and the information access. Transfer learning, that's the training scenario question. A feature extractor is pre-trained on clean data. It's then frozen, so we're not going to change that. And it's used while training just a linear classification head that we tack on to the end. It is also trained on a disjoint set of training data. That downstream data, that's what I'm going to call that, has poisons in it. Okay, so we also have from scratch training. So again, this is a change in the training scenario. We're not up to information access. The network is trained from a random initialization on data containing poison examples in the training set. This is sort of what you might expect when you talk about training a model on poison data. When it comes to information access, we are going to give the attacker access to the training data and one target image in all cases. That's always what it means to be the attacker, is you have the whole training set and you know your target image, your single target image. They also have access to model parameters in the transfer learning setting and the model architecture in the from scratch setting, provided it is a white box test. So there's white box and black box. And that information access in the second part here to model parameters and model architecture, that means it's white box. If you don't have that access, it's black box. When it comes to data sets, we are going to do a CFAR10 experiment, a CFAR10 test. So we are going to fine tune data on a subset of CFAR10. Your fine tuning data, excuse me, is a subset of CFAR10. The pre-training data that the feature extractor was frozen with is CFAR 100. So we're guaranteed that this is a disjoint set, at least when considering labels. The first 250 images per class and that will include your 25 poisons. So this is a small set of data, relatively speaking, right? The CFAR10 training data is 50,000 images. There are 10 classes, so usually there are 5,000 images per class, and we're going to allow 250. This choice was made to justify the use of transfer learning, right? If you're going to assume your victim is doing transfer learning, we need to have a realistic assumption that they benefit from transfer learning. And we did a small experiment on the side. It's in the supplemental work of this paper in the appendix. But we showed that at 250 images per class in CFAR10, you actually do better if you pre-train on CFAR 100. So that's why we picked this small data set. It also provides a small, quick evaluation setting for labs with even more modest resources. Excuse me. We also let the attacker insert 500 poisons when training from scratch. And again, that's the whole data set. So you get 500 poisons. In TinyImageNet, similarly, 100 classes of TinyImageNet are pre-training data. The second 100 classes are fine-tuning data, and you get 250 poison images. In the from scratch training, we train on the entire TinyImageNet data set with 250 images poisoned. I think that these details are rather hard to keep track of, and they are available in the paper. So don't worry so much. In the final table, I'll make clear which things are big experiments and which things are small. We also have to talk about architectures. If we want to have black box attacks and white box attacks, then we need a way to have different architectures. So we picked 3 popular models at the time that we were doing this. It seemed a natural choice for CFAR10 to deal with a Resonate 18, a VGG11, and a MobileNet v2. In a white box scenario, the victim's using a Resonate 18, and the attacker has access to that. And in TinyImageNet, we used a larger VGG16, and the black box tests are done on MobileNet v2 and Resonate 18. This is just designed for a little bit of variety so that it doesn't turn out that everybody's trying to make poisons for Resonate 18, if such a thing helped anyone. And finally, we'll talk about these benchmark scores. So now we get to this answer, this complicated, not one single number answer to how toxic is each poisoning method. The feature collision is never the best. This is not so surprising to us. It was the first one of the papers considered here. It considered only white box transfer learning, and it did a few other things in its experimental design that we removed. So its best performance in the white box transfer learning setting is 22% on CFAR10 and 49% on TinyImageNet. These are averages over a lot of trials. I can't remember exactly how many right now, but there are details about that and the error bars, the plus minus one standard error in the appendix of the paper, if anyone's interested in that. Convex polytope came out after feature collision. It claims to be better than feature collision. And in fact, on CFAR10 in the white box transfer learning setting, it is, but it's somewhat comparable, if not worse, in the other settings. TinyImageNet white box, it's worse, and black box and from scratch sort of similarly. A lot of the from scratch numbers are very, very low, right? Something that's 0.67% accurate. That means out of 1,000 trials, very few worked. We're not really bothered by that because these methods were never designed for it. They manipulate features. If you're learning from scratch, your feature space is going to change. So the low figures are, we should say, to be expected. They don't bother us. A bullseye polytope shows a very impressive 85% on the white box and 100% on the white box in TinyImageNet. That's pretty cool. Bullseye polytope is actually just a small change to the algorithm in convex polytope. That's the BP. There's Witch's Brew, which was designed for from scratch training. So we didn't even test it in the transfer learning scenarios. We just wanted to show that something that is designed for from scratch can actually perform at least sometimes. And the backdoor attacks in the bottom 2 rows again show that these things are not so successful in what we thought is kind of a standard testing scenario where if you were really trying to predict what your attacker does, you might make these assumptions. They're basically standard hyperparameter choices, things like that. So in the end of the day, I can't really tell you how effective each method is, But if you have a new poisoning method and you do these tests, so that's transfer learning, white box and black box, and from scratch on 2 different data sets, 6 things to try, you might find out that for one particular setting, you're better, maybe for all of them, you're better than existing attacks. And so unlike classification accuracy, where on CFAR10, there's a single test set, we actually have sort of a smattering of tests, right? An array of things you can try, and you might gear an attack towards one of them. That's a reasonable thing to do. If you are looking to attack a from scratch training setup, you might prioritize that column and you might not do better in the transfer learning. We felt that providing the community with this test bed made sense. And I'm curious to hear if anyone has things that they would have liked to see in a benchmark like this, or any other thoughts. I see that there are a couple of things in the chat. I apologize if I missed those a little while ago. So let me just show you that we're done here. My next slide says thank you, those 2 QR codes again. And I think while I have this slide up, I'll just read these questions out loud and see if I can remember the answers. Otherwise, maybe we'll go backward. So the first one says, I have a question, why the optimizer matters, to what degree, any insights on why? Thank you, Jim Feng, for that question. I don't think that I have a rigorous or a quantitative answer as to why, but we tested Adam and SGD, and the biggest difference there is that Adam has adaptivity. So typically, if you're using an adaptive algorithm, you're going to find a minimizer a little bit faster, maybe a little bit closer to initialization. I won't make any rigorous claims about how all of that works, but those things tend to be a little bit more vulnerable. I think you can sort of chalk that up to the idea that stochasticity without the adaptivity might sort of wash away some of the details of your training data. And again, it's not super rigorous. We didn't play with that. We didn't test that more carefully, but that's what I think.
I got it. Thank you.
Yeah, you're welcome. The other question I see here says, how transfer learning is important. I want to know how backdoor attacks and transfer learning are correlated to each other in a real world scenario. I'm not sure exactly I understand. Are you wondering, like, in the real world, how often people do that in a transfer learning scenario? That question is from Naoto.
I'm sent that question. So my question is with so there are many papers discuss transfer learning based in the context of backdoor attacks, and I wonder if to be honestly, discussion on transfer learning for backdoor is necessary or not, because so in case of poisoning attacks, so for instance, so on collaborative learning or federated learning, each submitter can send poisoning data inspect of clean labels. So for like this, is there any scenario of transfer learning and backdoor attacks? So I want to know just so any example about transfer learning and backdoor combination of transfer learning and backdoor attacks.
Okay, I think if I understand your question, you're pointing out that if the victim is doing transfer learning, then maybe the attacker doesn't have the option to change the test time data. Is that the question? Mm-hmm. Yeah, that's a good question. I haven't really thought about how practical that scenario is. There certainly are papers that propose backdoor attacks and test them in the transfer learning scenario. So I sort of took them at their word that that was a threat that existed. But I appreciate the question of, is that a real practical threat? I'm not sure that I see why somebody doing transfer learning would be more secure to this. Yeah, can you say a little bit more about why the victim in that case is not vulnerable?
Yeah, if you can tell us. So yeah, but I understand. Anyway, so backdoor attack is important as understanding attack surface or machine learning security. Yeah, I just to get my precious question, my critical answer from you as your response. Thank you.
Yeah, thank you for the question.
All right. The talk is very exciting. We very appreciate. It's track many interesting questions. When I hope when the situation is lifted, we can welcome you. Avi and Chin can come visit us in our Nihon Bashi Center in the Tokyo. It's a really nice place in the center of the Tokyo and near the Senza place. All right, thank you,
Thank you.
again for give us talk. Hi, Chin. Can you want to share your screen? Yeah.
Yep.
Okay, I'm going to introduce Chin a little bit. Chin Zhu is a PhD candidate at the University of Maryland, College Park. His advisor is Professor Tom Goldstein. His research focuses on developing better algorithm to enhance accuracy, efficiency, robustness of neural network for application on computer vision and natural language processing. Before coming to UMD, he obtained his master's degree from Shanghai Tech University, where he worked with Professor Ke Wei Tu and Professor Yi Ma, and a bachelor degree from Beihang University. Meanwhile, he has worked as a research intern at Google, NVIDIA, Microsoft, Baidu, and Intel. Hi, Chin. You can get started your presentation.
Yeah.
You're talking.
Yeah. Thanks, Jianfeng, for the introduction. Can you all see the full screen presentation now?
Yes, I can see your screen and also can hear your voice.
Okay, great. Yeah, so today I'm going to talk about our work on using adversarial training to improve the generalization of these neural network-based models on various different domains. So I think everyone here is probably very familiar with the notion of adversarial training, but let's just revisit it a little bit so that we are on the same page. So adversarial training is a very effective method to defend against adversarial examples. So it has been found a long time ago that neural networks are prone to label preserving adversarial examples, which means that, for example, for image classification, we can add some very small perturbations that are imperceptible to humans, but it can change the prediction of these neural network-based classifiers. And for natural language processing, similarly, we can find some semantically equivalent rules. For example, we can just use some abbreviations of the original sentence or just adding some punctuations that do not change the meaning of the original sentence, but it can change the prediction of the neural network-based classification models. So, to counter against such threats from adversarial examples, we have developed techniques. The most effective one is adversarial training. So basically, it tries to solve a min-max problem, where the inner max problem is to generate some perturbation delta within some norm constraint S that can maximize the loss function of the neural network. And the outer main problem is just to minimize the loss of the perturbation that causes the maximum loss. And it's optimizing the parameters to achieve this. So perhaps the most simple and effective approach is the so-called projected gradient descent. It's just this name, but it's actually doing the gradient ascent for the inner steps. So basically, this algorithm just alternates between k steps of gradient ascent to generate the perturbation delta that can maximize the loss within the norm constraint. And the most prevalent or popular one we have seen is the so-called signed gradient, fast signed gradient method. So why it is using the sign of the gradient? That's mainly because it's using some convex approximation to this loss function, and then in this case with the L infinity constraint, the simplest direction is just to take the signed gradient steps. And if we find this perturbation to have exceeded the norm constraint, we just do some clipping to project the perturbation back onto the norm ball. So after this case steps of gradient ascents, we will get this perturbation delta k. We just use this perturbation and add it to the clean input and compute the loss, and we do a gradient descent step on this perturbed image to update the parameters. So so this PGD-based adversarial training has been found to be very effective for improving the robustness of convolutional networks for image classification. So so from this plot, we can find that the blue density or the frequency curves here corresponds to a naturally trained model that is perturbed using PGD with a very small norm constraint. We can see that from tens of thousands of random starts, if we perturb the images, the naturally trained networks tend to be easily to have a very large loss. While for the red curves are the results from models that has been trained with PGD, and its loss remains closely to 0, which means the model is very robust. However, the drawback is that it has been widely observed that for image classification, if we do adversarial training, then the accuracy of the model on the clean data tends to drop no matter on what data set. So at that time, we are wondering what happens if we apply adversarial training to other domains. So so intuitively, adversarial training is just trying to find a max margin classifier, which should be having better generalization, but somehow on the images, it seems to be showing the contrary. So, and now we know that with some handling of the batch norm statistics on the clean and adversarial examples, we can use adversarial training to improve the accuracy on clean data too. But at that time, it has not been super clear about this point. So yeah, so today I will, the main content I'm going to introduce today are 3 of our previous works. The first one is to using a enhanced adversarial training algorithm to improve the generalization of transformer-based language models on natural language understanding. The second work considers both the pre-training and the fine-tuning stage of the transformer-based vision and the language models. And we found adversarial training used during the pre-training phase can also improve the generalization of these models on vision and language tasks. And the third one is we find that this adversarial training can also be used to improve the generalization of graph neural networks on 3 different types of graph-related tasks. So yeah, here I'm going to introduce the first work, which is about using enhanced adversarial training to improve natural language understanding. So this work was done during my internship at Microsoft. So before considering whether adversarial training can improve the generalization or not, actually the data efficiency can be very important for language understanding. So this language understanding, for example, it considers tasks like sentiment analysis or comparing whether 2 sentences have similar meanings. Usually it has can have hundreds of different types of language related tasks, and it can be in hundreds of different types of languages. And it can also have numerous domains. For example, the emotion analysis can be used for movie reviews or just product reviews. So considering all these different configurations and the numerous different language understanding tasks, each of the tasks can be label hungry, and we cannot simply make them better by doing some supervised training at a very large scale. But actually, developing an effective and efficient data augmentation for language can be quite challenging. The main issue is that language can be more tricky than images. For example, if we add some perturbation to the images, we know that if the perturbation is small enough, it won't be very obvious and won't change the class, for example, of the image. But for languages, even if we flip a single word and replace it with some synonym of that word, it can change the meaning drastically. So, so there are some previous works for that is similar to adversarial training for on the language data. So most representative ones are, first is the semantically equivalent adversarial rules, which searches for the semantically equivalent rules that can maximize the loss of the models. And so this type of method can guarantee that after the transformation, the meaning of the sentence is not changed, so that the label is preserved. However, when we use the examples generated by such rules to train the models, we find that it does not always improve the accuracy. For example, in this sentiment analysis, after adding these augmented examples, it actually reduces the accuracy. The other type of methods tries to use gradient methods to find the best word flipping and change them into the synonyms or just clauses in the embedding space. However, to guarantee the meaning of the sentence is not changed or the label is preserved, they also might require some additional pre-trained language models to see if the meaning of the two sentences are the same. So this method is very ineffective. So perhaps a more effective way of doing adversarial training for language is to add adversarial perturbations to the embeddings. So in this way, similar to the images, if we know the perturbation is small enough, then we know it should preserve the meaning of the sentence. So, but we have already observed that the adversarial training can hurt the accuracy of CNNs. However, adversarial training actually can improve the test accuracy on the clean samples if it is used to the embedding space of recurrent neural networks. So, but now we don't really use RNNs that much for language understanding. So we're just wondering whether the effect is because of the difference in the domain or the difference in the model architecture. So does adversarial training in the embedding space improve transformer-based models? The answer is yes. If we simply use this standard PGD-based algorithm on the embedding space, it can improve the Roberta model, which was a model very similar to BERT and was almost the best at the time of the work. If we just do this at the fine-tuning stage, we can improve it, the results on many of the downstream tasks. However, the improvement is quite marginal. So, so the problem we want to solve is that given the same training budget as PGD, how can we make adversarial training even more effective? So PGD introduces lots of overhead. So we will want it to improve the results more significantly. So the way we are approaching this problem is to consider some efficient adversarial training algorithms, which were just proposed during that summer. So so this there were mainly two representative works, and they have something in common. So their general idea is that they want to make better use of the backpropagation process in every gradient sense step, so that we can reduce the total number of backpropagations. So what does this mean? So so when we are doing gradient ascent, we want to get the gradient of the inputs. In this process, we will need to also compute the gradient of the loss with respect to every of the feature maps. However, most of the current deep learning frameworks like PyTorch, it will by default compute the gradient of both the feature maps and also the gradient of the parameters. So actually, during this process, we can also get, when we are computing the gradient of the input, we can also get the gradient of the parameters at no computational overhead in practice. So So considering this, the adversarial training for free, or what we call free AT here, is simply doing this. So for example, for the same mini batch, in the original PGD algorithm, we had to do k steps of gradient ascent on the input perturbations. And after the k steps, we compute its loss and do one gradient descent step on the parameters to update the parameters. So free AT tries to accelerate this process by doing, so when we are getting the gradient of these perturbations, we can also get the gradient of the parameters for free. So in this way, after the gradient ascent of the inputs, we can also do one step of gradient descent on the parameters. So so if we keep the total number of forward backward passes unchanged, then we can use the same amount of training time as SGD. But with free AT, since during the process we are also optimizing the parameters to minimize the loss on the perturbations, we can also get the robustness almost for free. So here is the result of the free AT. So we can see that when we use 8 steps of gradient ascent, and in this way we are replaying each batch for 8 times, it can get some very similar or even higher robustness than the standard PGD trained network. However, its clean accuracy compared with PGD on natural images are lower, mainly because the loss of the specificity of the SGD optimizer due to the replay. And another perhaps obvious drawback of free AT is that it has this still send steps issue. So if we look at its optimization process, for example, this delta 1 is actually from the gradient with respect to the parameter θt from the last step. However, when we are using delta 1 to compute the loss, we have already updated the parameter into θt plus 1. So in this way, since the parameter has already changed, the perturbation might not be the optimal for this changed parameter. So so in this way, it might indicate that we have not achieved the optimal robustness with free AT. So so another method that was proposed almost at the same time is the so-called YOPO. So this method, the general idea of this method is to restrict most of the forward and backward propagations within the first layer of the network during the ascent steps or when updating the adversaries. So what does this mean? So if we look at this plot here, the left part represents the input to the network, and the right part here is output of the network. So when we first do the forward pass to compute the loss, and we do a backward pass to compute the gradients. And after this process, we also retrieve the gradient of the first the feature map immediately after the first linear block of the convolutional network, and we keep this gradient a constant. And in the later steps, it adds an additional inner iterations to further update the adversarial perturbations. And during these inner iterations, it's keeping this gradient of the first layer's feature map as a constant. And it also recomputes the Jacobian of this first layer's feature map with respect to the input, and multiply that with this constant gradient of the feature map. So so in this way, it argues that these n steps of additional inner iterations can further improve the strength of the adversarial examples while without much computational overhead. However, if we revisit this process, since this gradient is a constant, And also it's computing the Jacobian of just the first linear layer. So this Jacobian is also a constant. So we are equivalently just doing the same step in exactly the same direction for an additional times. So if we do not have the non-constraint, then this is just equivalent to using a larger same step size. Or it means all the difference from Yopo is just because of the non-constraint here. And we divided a larger step size into multiple smaller step sizes. So I just feel this step seems to be redundant. So can we think of an easier approach that can both remove the redundant steps from Yopo and also avoid the still ascend step problem? The approach we finally take is actually very simple. So here, this green arrows just represents the additional inner steps from Yopo. So we just remove all these green arrows. And we, similar as the free AT, or Yopo, we are getting the gradients of the parameters during every gradient ascent step. However, different from free AT, we do not update the parameters immediately. We just accumulate the gradients. And then after all the case steps, we use the accumulated gradients to update the parameters. And obviously different from Yopo, we remove the inner steps. So we do this comparison of Yopo and the simplified approach on these different language understanding tasks. And we are training a transformer-based model. So for Yopo, in our setting, we are defining the first transformer block as for its inner iterations. And since its inner iterations might be equivalent to using a larger step size, we consider two settings. In the first setting, we also divide the inner step size of Yopo by the total number of inner steps. And then in the second setting, we are using the same step size for the inner step of Yopo as we use for our method. So in both cases, we find that without the inner steps, actually, the model can achieve better performance. And we also have results comparing with free AT, where we kind of avoid the still gradient ascent step issue, and we can have better results than free AT. And we can also do better than PGD using under the same training budget. So the main intuitive explanation is that when we are doing this gradient accumulation, we are effectively trying to minimize the loss of k different adversarial examples that have different sizes surrounding the clean embeddings. So in this way, we are can somehow be similar to constructing k sets of different transformations. And there's some previous theoretical work showing that if we train a model to be invariant to a set of t transformations, then the model can have up to like square root t smaller generalization error than a non-invariant model. So that might explain why we can do better than PGD, because PGD is only training the model to be optimal to the perturbation with the largest perturbation size. So another perhaps trick or something we find useful during this process is that we should pay attention to the dropout mask when applying adversarial training. So these transformer-based models are usually trained with dropout. So by default, when we are doing the gradient ascent steps, since we also need to do forward pass, the dropout mask actually changes in every forward pass. So so different dropout pass masks can correspond to equivalently a different neural architecture. So to enhance the adversary, we should probably fix the dropout pattern in every ascent steps, so that percent steps are actually maximizing the loss for the same architecture, and the perturbation can be optimal. So we compared the case where we fix the dropout mask at the beginning of each mini batch, and the other case we didn't handle this dropout mask, and we can see further improvements from here. So here are just some comprehensive results. So after applying this method to the Roberta model, we can further improve Roberta model and achieve the first place in the group benchmark at time of submission. And we also showed that the method is also effective to other language understanding tasks, which mainly involves question answering. So yeah, so that's basically everything for the language understanding part. And for the second part, I'm going to talk about how to use enhanced adversarial training algorithms for vision and language tasks. So in this work, we also achieved some good results for a variety of vision and language tasks. And the three key ingredients of this work, firstly, is that we are using adversarial training to both the pre-training and fine-tuning stage. So we are, I think we were the first work to adopt adversarial training to these transformer-based models during the pre-training stage. Another thing is that we were adding perturbations in the embedding space of both image and text. So in previous works, we have found that adversarial training on the images might harm the performance of the model. But here, these transformer-based models are extracting the object embeddings from the images first with some detectors. And we find that if we just add the perturbations to the embeddings, it can still improve the results. And the third one is an enhanced adversarial training objective that we found to further improve the performance compared with what we were using the previous work. So yeah, so in detail, so actually we find that even if we just use adversarial training only to the pre-training stage, and we fine-tune on this downstream task without any adversarial training, the result can still be better than starting from a model that has not been adversarially pre-trained. So so the intuitive explanation is that the pre-training and fine-tuning tasks can be inherently correlated. So for example, in the pre-training stage, we considered some masked language modeling objective where we randomly masked out some tokens from the caption of the images. And then we asked the model to predict the masked out tokens. So for example, if a downstream task is VQA, then these masked tokens might be just the answer to the question. So so when we are doing adversarial training, it can also help us to start the later fine-tuning stage at a better region from the pre-training model. And we also find that the fine-tuning using adversarial training to the fine-tuning stage can result in more significant improvement than using adversarial training just for the pre-training stage. So and using both has the using adversarial training at both stages has the best results. And the second ingredient is about the exploration on what's the best way to add the perturbation to the embedding space. So yeah, as we have previously mentioned, it looks like if we add adversarial perturbations to the raw images, we can often see adversarial training reduces the accuracy on clean data. And also, but instead, when we are adding this perturbation to the embeddings of the images, even if we don't perturb the text data, we can still see the improvement in the final performance. And similarly, as our previous work in the text domain, it also makes more sense to add adversarial perturbations to the embeddings. And another thing we observed is that instead of adding this. So all this task comes with the image embeddings and the text embeddings. However, we find it's better if we add the perturbations to the image embeddings or the text embeddings separately, rather than generating the perturbations for them simultaneously. And we find this to empirically give better results. So the third part is enhanced training objective. So in this objective, we consider a regularization that promotes the consistency between the clean samples and adversarially perturbed examples. So, to be more specific, in the we have mentioned that we are adding the perturbations to the image embeddings and text embeddings separately. And when using this consistency regularization, or which is just a KL divergence between the clean samples predictions and the adversarially perturbed examples predictions, we are perturbing the images and text separately. And then we will have two sets of KL divergence regularizations. So, so we compare with our previous approach where we only consider the original training objective as we are doing natural training, for example, the cross entropy loss of this maxed out token, which corresponds to the second line here. We find it to have a less improvement than we are doing this KL divergence based regularization. So, and this regularization actually improves the result significantly, even compared with the second line where second row where we already are using some sort of adversarial training, and it's significant for both the large and base models. So here we just show some results on a variety of different benchmarks, where we can see that for this different vision and language tasks, we can all improve the final results compared with the same backbone significantly. And we can have a closer look at the effect of the pre-training and fine-tuning. So for example, when we are only using the adversarial training for the pre-training stage, we find it to improve the accuracy by 0.5 on average. And however, if we just use it during the fine-tuning stage, the accuracy improves further by 0.8. And if we use it for both, we can further improve by like 1.15 on average for all these different tasks. And we can see that if we do this adversarial pre-training for more steps, the improvement seems to become more and more significant. So this indicates that we can do this adversarial pre-training at a larger scale than we were considering, and get even more improvements. However, actually adversarial training itself is quite expensive. So yeah, it's worth considering how to scale it to larger data sets and training for more iterations. And another thing here is we didn't only consider this uniter-based backbone. We also consider other backbones, and we find adversarial training to also improve the result of other backbones. So it's not just restricted to one architecture. So in the last part, I am going to briefly introduce our recent works on using adversarial training as a data augmentation for graph neural networks. So for graph neural networks, there has been a lot of data augmentation methods, but all the previous methods has mainly been focusing on perturbing the structures of the graphs. So for example, you think we have this neighbor sampling, or we randomly drop some edges from the graph, or we add some virtual nodes, or even we permute the nodes. However, if we consider there seems to be fewer works considering perturbing the node features as augmentation. So if we can have some good results in this direction, then it can be complementary to all the previous works of structure-based augmentations, and we can further improve the generalization of these models. So there are a few previous works that have been using similar ideas like adversarial training to perturb the node features and as a type of data augmentation. However, these methods are not scalable. The main reason is that so graph neural networks depends on message passing, but these methods, when they are perturbing the node features, for each node, they are assuming the other nodes are not perturbed. So in this way, we had to create different adversarial perturbations for each different node. So it's hardly scalable to large graphs. And all these methods were only tested on some small node classification tasks. And how to improve their scalability? So in our work, the biggest difference is that we do not require all the other nodes to remain unperturbed when we are doing generating the adversarial perturbations to the node features. So in this way, we can perturb the nodes simultaneously. And these previous works also did not explore whether perturbing the node features can also improve the graph classification and link prediction, which are two other important tasks for graph. And another thing is we consider how to further improve the efficacy of adversarial training, which means to get more accuracy after this process. So a brief introduction to this idea. So what we are doing is still solving a min-max problem as we were previously doing for adversarial training. So we do not consider the KL divergence-based regularization here. And when we are solving the inner max problem, we are using PGD-based gradient sense steps to perturb the node features, which is more similar to perturbing the image pixels. So the main observations or contributions of this paper is two parts. The first part is we adopt a very similar approach as the previous FreeLB method, where we accumulate the gradients of the parameters during every gradient steps of the input perturbations. So in this way, for each node, we are actually using the perturbations at different sizes to train the model and becoming invariant to different sizes or multiple scales of perturbations. So if we visualize the adversarial perturbations, the norm of the perturbations used to train these models, we find that using our method, we are actually training the models at a more diverse set of perturbations at different sets, while the PGD-based methods are all concentrated at almost the same size. So our method, when we are doing the third step, we find the scale to be more scattered. So this can further improve the generalization, as we previously mentioned, for language understanding. And another interesting finding is that we find if we use different scales for the labeled and unlabeled nodes in this node classification task, then we can further improve the performance of our method. So for node classification during training, there's an unlabeled nodes, and these nodes are only used for message passing for prediction of the labeled nodes. So so it seems reasonable that we are relying more on the node features of the node itself rather than its neighbors. So and these unlabeled nodes are usually just neighbors during pre-training, during the training stage. So we can actually using larger perturbations for these unlabeled nodes. And here we show the plot under different ratios of the unlabeled versus labeled node perturbation sizes. So if this log ratio is larger than 0, it means we are using larger perturbation sizes for the unlabeled nodes. And we find that if we reduce the size of perturbation on unlabeled nodes, the result becomes worse. But if we increase the size of perturbations on unlabeled nodes, then we get better results. So here we visualize the test accuracy throughout training, and we find with this adversarial training, actually the model converges much faster. And so in all our previous explorations, we are actually keeping the training budget the same as PGD. Here we also did explorations to see whether we can also reduce the total number of forward backward passes and keep it the same as a baseline, which means we will using exactly the same approach as the adversarial training for free method. So here the free method is having the same amount of forward backward passes as the baseline, and the flag fast is also using the same setting. So we can find that using this gradient accumulation based method, we can have more improvement than the free based method. So here we just show some comprehensive results for different graph neural network architectures and different benchmarks, where we find the model to find our method to uniformly improve the performance on all these different settings. Yeah, so that's basically everything I wanted to introduce. And personally, I feel the conclusion here is that adversarial training is a useful and complementary tool to further improve the generalization when we have only a limited amount of label data. So, so it's always something you can use to further improve your model. And we have seen other works, or what we have just showed, that adversarial training can actually improve the generalization for many different domains, includes image classification, which is from the ADV prop paper. And we have showed it also improves for language understanding, vision and language tasks, and graph-based tasks. And however, maybe the biggest drawback is that currently most of the adversarial training algorithms seems to have low efficiency, which means we still have to use like at least 2 or 3 times training budget as natural training. So their efficiency needs further improvement. Maybe we can improve it from both the perspective of system design or just from the algorithm itself. And there have been some interesting recent works in this direction. Yeah, thank you for attending today. That's everything I wanted to talk.
Thank you, Chen, for your great talk. It's really exciting. Yeah. Chen, I see several questions coming up.
Yeah. So thanks, Andrew, for the question. So the question is, can you discuss have more discussions on the 2 facts? First, adversarial pre-training improves the representation transferring, but the adversarial training on training set degrades the test accuracy on the validation set. Yeah, so I think, oh, sorry, that's my draft. Yeah, so I don't know if you mean these 2 facts are related, and I think the second fact is from our previous observation that adversarial training will reduce the accuracy on the test set for image classification. However, there have been some follow-up work showing that during training, if we use a different set of batch norm for the clean examples and adversarial examples, then the accuracy on the test set can also be improved. So I think this part is still a bit unclear to me, whether it is because of the difference of the domains or if it is because of the use of batch norms in these image classifiers or the convolution networks. I also did some experiments previously, like if we just do adversarial training for a convolution network without batch normalization, it still does not seem to really, it will also reduce accuracy on the validation set. So to me, I would feel it's more of an issue of the domain, maybe it's a difference between the image domain and text domain. And in our later results of doing the pre-training or the representation transferring on this vision and language tasks, yes, we involved text image data here, and we also find that adding these perturbations to the image embeddings improves the performance on the downstream task. However, I think maybe the difference is there's still some difference here in that we also have the text embedding in this process. So it's really hard for me to really say I have a very clear answer of why it has a difference in different domains. But what I want to say is here, in the pre-training we are considering here, we are doing vision and language tasks. So we also involved text data. So it will be interesting to see if we can find an architecture or easier training process that can make the adversarial training also improve the test accuracy for image classifiers. So yeah, I don't know if I answered that question. Yeah, thanks.
I see. Very appreciate. I basically have a question for, I know adversarial training kind of like a smoothing using the augmented data to smooth the the weight space, for example, or the input space. Would be this is the reason for that we can improve the performance some way?
Yeah, to me, adversarial training, it does improve the smoothness, maybe the loss landscape on the input space, because it's training the model to be less sensitive to the perturbations of the input. But my intuition still comes from the comparison of large margin classifier versus a smaller margin classifier. So if the adversarial training generally makes the in the input space makes the hard examples further from the decision boundary. So in this way, even if the distribution of the test data shifts more, then we can still have maybe better generalization because of the large margin. So yeah, so that's my intuition, but I don't know if that's a great.
Right. Yeah, that's perfect. That's perfect. Yeah, it's really convincing. Yeah, thank you. All right. If there is no further question coming up, this is the end of today's seminar. Again, we really appreciate Chen's and Avi's great talk in our center. Thanks again. Hopefully in the future, we could welcome you in the Tokyo, in our Nihonbashi office when the situation is lifted. Thank you again.
Yeah. Thank you. Thank you for having us today. Thank you.
Sure. It's our pleasure. Bye-bye.